Unit 3.5, chemical bonding, and more specifically today, talking about polarity. Polarity. How do we know if something is polar or non-polar? Well, a non-polar bond means that the electrons are shared equally. I like to call these non-polar equals no polar. It's not really great grammatically English, but non-polar means that nobody is pulling harder than the other. Everybody's pulling equally. It is in some cases, a 4-team tug of war. A 4-team tug of war trying to get the electrons closer to them. A non-polar means no team is pulling harder than the other one. It's equal. The pull is equal amongst all bonds. A polar bond has polars. The electrons are not shared equally. It is a tug of war that somebody is going to win. Somebody pulls the electrons closer to them. And yes, it can in some cases be a 4-team tug of war. To think about this in not, chemistry terms, we can think of it as if you've ever had to share something with somebody. Such as if you are a sibling, you or one of your siblings have to share a car. Which always seems that somebody is not getting an equal share. When we have an equal share, there's nobody pulls harder than the other. Everything's nice. The car doesn't seem as if it's one person's more than the others. The electrons don't seem that they're another element's more than the others. But most of us live in the real world, and if you share a car, chances are it's not shared equally. Because of the unequal share, you have a polar. Somebody gets the car just a little bit more often. Therefore, they are the polar. The polar. They get a little bit more of those electrons a little bit more often. So polarity of the bonds is one way. I don't like it. I prefer looking at it in the molecular shape. What does it look like? In the movie Field of Dreams, they say if you build it, they will come. Well, when it comes to polarity, if you draw it right, polarity will be seen. You will see the polarity if you draw it out right. Correctly, I mean. The molecular shape and everything from there can be easily determined through drawing them out correctly. How do you draw them out correctly? Well, that's what we've been kind of practicing. Now, sometimes that doesn't get you the right answer. Sometimes drawing it out correctly, there's just some little weird things that happen. But you know what? If you draw it out correctly, you will probably be able to, within a like 95 percentile, be able to comment on the polarity correctly. 5% of the time, there's these weird things, these exceptions to the rules, right? Like we haven't had to deal with those before. Kidding, right? It's chemistry. We have exceptions all the time. But that's what it becomes. The exceptions are kind of the, that's why. Okay? But if we draw them out correctly, trying to figure out the electronegativity becomes a thing. And the polarity, the actual polarity of the bonds is just that. Using electronegativity, subtract the two, it falls in this range, it's a polar bond. Time is money, right? And according to Biggie Smalls, more money, more problems. Okay, so more time is more problems when you think about it. Idle hands are the devil's work, right? So you have that polarity gets, and even polarity, calculating the polar bonds can be harder. Because you have to know the range that it has to fall in. I think for my goal for most chemistry students is comment on be able to draw it out, comment on the polarity. And chances are 95% of the time you're going to get it right. It's the ones that our homework, Mastering Chemistry has, that makes you like, oh, that 5% stuff. The majority of the stuff that you will need to worry about, you should be able to just be able to draw it out and look at it and go, oh, that's what it is. Okay? And here becomes the thing. And we remind ourselves of this. If a molecule has all nonpolar bonds, it's nonpolar. Nonpolar means no polar. Nobody's pulling harder than the other. Because once you have a molecule or a part of a molecule that is going to have something that pulls, if you can identify an element that is a puller pulling harder than any of the other things, it is a polar. And the symmetry is a big part of that. Okay? Symmetry is a big part of it. Drawing them out symmetric. Drawing them out symmetric as possible is a big part of what we need to do. But if everything is nonpolar, everything is right as rain, no polars. But once you have one thing pulling harder than another, now you have a unequal pull. You have a tug of war match that is not equal. You have a polar. You're going to have a team that wins the tug of war match. So let's look at one. Remember the rules. That's symmetric rules. Drawing them out correctly. If they're drawn out correctly, the symmetry makes sense. If we draw them out correctly, we can see how they're supposed to look. And we look at the molecule that is how it's drawn on the left is correct. Drawing it out on the right way, the not way, makes it difficult because if we draw it out that way, it looks like the chlorine are pulling equally on each other. It looks like the hydrogen are pulling equally on each other. However, when we look at a three-dimensional model of it, that's why the symmetry version on the left-hand side mimics what we see in the three-dimensional model, and that the chlorine are not pulling away from each other, and that they are actually pulling opposite of the hydrogen. So the chlorine look to be pulling this direction here, which they are, which is opposite of that of the hydrogen, meaning these chlorine are pulling, therefore it's polar. In the one on the right, it looks as if these chlorine would cancel each other out, and that the hydrogen would cancel themselves out. But this does not have symmetry. Because it does not have symmetry, it doesn't allow us to look at the model. And this is why I think the ability to build the molecular models is of the utmost importance. What does it look like? So that we can see those changes. So let's try a few of these out. Again, some of them, we will not just comment on their polarity, but we will also try to quickly also comment on their geometries, as that would be good practice. Molecular geometry, electron geometry. It will show up. So, for my first one, I have methane. Methane is going to have my carbon in the middle, and then my hydrogen around it. So for methane, everything is there. I have 4 regions, all of which are bonding. It is tetrahedral. Because all 4 regions are bonding, the molecular geometry is also tetrahedral. I think I spelled that wrong. We'll get to it later. And everything is pulling the same. So since it's symmetric, nonpolar. Everything pulls the same. Now, for water, I've always said this is a matter of life and death, a number of times, to the point that I think some of you are starting to question me. And that water has 4 regions, but not all of them are bonding. Therefore, it is bent. And here's a little trick. Notice how the electron geometry and the molecular geometry are not the same. When that happens, you are almost guaranteed polarity. If it's the same, then you have to really look at what's there. So for carbon dioxide, people now look at it and say, well, which one do I look at? The central atom. The central atom here has two regions, both of which are bonding. Because the electron geometry and molecular geometry are the same, with the same elements, nonpolar. And the last one, I even draw it out to indicate some of the polarity. It is tetrahedral. The molecular geometry, I believe, is trigonal pyramid, or trigonal pyramidal. And is definitely polar. Even because there's a couple things, you only have hydrogen, but it's those non-bonding electrons that push the other ones down, does not allow for equal pole.